In part 2 of our chapter 18 lecture, we're going to talk about the synthesis of aldehydes and ketones. The synthesis reactions uh, basically are mostly going to be oxidation reactions, but we will see some reduction reactions later. Many of these are also going to be reviewed from a previous chapter. So for example, reaction A, oxidation of alcohols to aldehydes and ketones. These were reactions that we discussed back in the alcohol chapter as reactions of alcohols. Now we're going to look at them from the point of view of using them to make the types of products that we would like. There's two observed reactions that we need to learn. The first one is a reaction that oxidizes primary alcohols up to aldehydes. We have to use a primary alcohol to make an aldehyde because primary alcohol will be at the end of a carbon chain and aldehyde will be at the end of a carbon chain. To do this, we use this reagent right here, PCC. PCC is an acronym that stands for pyridinium chlorochromate, and that actual substance is created by mixing CrO3, hydrogen chloride gas, and pyridine. It forms an orange solid and is anhydrous, has no water in it. That's important for it to stop the oxidation at the aldehyde state. For our purposes, you can just use the abbreviation PCC. Most organic chemists will know what that stands for. In order to make ketones, we're going to need to start with a secondary alcohol because we need to have two carbon groups already attached to the carbon that would become the C double bond O carbon. In this case, we're going to use chromic acid, which we form from sodium dichromate sulfuric acid, so Na2Cr2O7 H2SO4. This chromic acid reagent is generally called the Jones reagent, and in fact, you can just write Jones reagent in most circumstances, and most organic chemists would know exactly what you meant. This is going to oxidize that alcohol up to a ketone and stop. However, it is important to note that Jones reagent cannot be used to make aldehydes. Unfortunately, if you try to make an aldehyde, it doesn't stop at the aldehyde oxidation state. It continues moving the oxidation state to the right, and you end up with carboxylic acids. Our second synthesis of aldehydes and ketones is going to use what we called ozonolysis. This is a review from our alkenes chapter. Ozonolysis starts with an alkene. We put in ozone gas, O3, and then we use a reducing agent. The most common modern one is dimethyl sulfide, so CH3SCH3. In older textbooks, you might sometimes see zinc and acetic acid. What this does is it essentially just cleaves the double bond into two double bond halves and then inserts oxygen into the break between the two double bonds. This will produce an aldehyde if the original alkene carbon already had a hydrogen attached. If, in contrast, the alkene carbon had two carbon groups, this will produce a ketone. Our next synthesis reaction is going to be the Friedel-Crafts acylation. It's a very specialized reaction. It synthesizes phenyl ketones. In other words, ketones where the carbonyl carbon has a phenyl group directly attached, and then some other carbon group on the other side. This was a reaction from chapter 17 this semester, so hopefully you guys remember it. And what we do is we use an acid chloride, and the acid chloride, the carbon group of the acid chloride is going to become one of the carbon groups of the ketone. We put in aluminum trichloride and benzene or a substituted benzene with the restrictions that we already talked about in chapter 17. And at the end, the chlorine is replaced with the aromatic ring. Our next reaction is the hydration of alkynes. This was a reaction that we discussed in the alkynes chapter. We start with an alkyne. We treat it with HgSO4, which is mercury 2 sulfate, H2SO4, which is sulfuric acid, and water. What happens in this reaction is that one of the carbons gets two hydrogens attached, the other carbon gets a double bond O attached. In general, this works best with symmetric alkynes because we have no control over which carbon will get the C double bond O. And so therefore, if the two carbon groups are different, you will get constitutional isomer products. The one exception to this is when we have a hydrogen on one end of the alkyne, and in that case, this follows Markovnikov's rule. We get two hydrogens on the carbon that already had a hydrogen, and then we get a double bond O on carbon 2. So we can specifically put the carbon double bond O at carbon 2 of the chain. A related reaction is the hydroboration of alkynes. In this case, what we do is we use a sterically hindered borohydride compound, so dicyamyl borohydride, for example. And this ends up putting hydrogens on the second carbon of a terminal alkyne and a boron, which is later oxidized up to a ketone on the end carbon. So what we get at the end is we get an aldehyde. The reagents are shown right here. They're very similar to the reagents for hydroboration oxidation from the chapter on alkenes. Finally, we have one new synthesis reaction. This reaction starts with an acid chloride, very similar to Friedel Crafts acylation. And what we're going to do is we're going to replace the chlorine with another carbon group. So that therefore the C double bond O would end up having original carbon group on one side, a new carbon group on the other side, and it would therefore be a ketone. The reagent we're going to use is this. R prime 2 CuLi. This is called a lithium dialkyl because there's two carbon groups, cuprate. Only one of the carbon groups gets transferred, the other carbon group is wasted. In advanced organic chemistry, one of the things that they have developed is the ability to specifically put only one carbon group that they know would be transferred and then another non-transferable group to make this work and not waste your carbon group. We don't need to worry about that. The lithium dialkyl cuprate is pretty easily formed using copper iodide, copper 1 iodide, and two equivalents of the corresponding alkyl lithium that has the carbon group that we want. So in this case, two equivalents of R prime minus Li plus. If we work out the stoichiometry of this, both of the carbon groups get attached to the carbon. The carbon gains a negative charge, keeps the lithium ion one of the lithium ions in order to balance that negative charge, and then we get a byproduct of lithium plus iodide minus. Cuprates are actually very useful for other reactions. For example, what they do is they allow carbon minus to act like a nucleophile on alkyl halides and acyl halides, in other words, acid chlorides. So for example, if we look at this potential SN2 or SN1 substrate, we have cyclopentane attached to a chlorine, we can treat that with di and propyl lithium cuprate. What we will do is we will end up replacing the chlorine, the halogen, with one of the propyl groups. So we've made a new carbon-carbon bond and we've attached this carbon chain to our original carbon substrate. If we look at the overall transformation, we can see it looks very similar to an SN2 reaction, where we take a carbon nucleophile and we essentially replace a halogen leaving group. However, I should point out it does not follow the SN2 mechanism. In fact, it has a fairly complicated mechanism that involves free radicals. If we were to attempt to do this with other carbon minus reagents, so for example, a Grignard reagent is a reagent that has a negative carbon alkyl group that could act like a nucleophile. What we would see is that Grignards and alkyl lithiums are too strong of bases. They're very strong bases. And if we go back and look at our nucleophilic substitution elimination table showing the preference for various substrates, we would see that very strong bases prefer to do E2 reaction with secondary substrates. And so therefore, we would do E2. This would be alpha. One of the adjacent carbons would be beta. We would end up with a double bond. And the base would remove the beta hydrogen, which would effectively protonate that Grignard and render it just an alkane, which is not a very useful substance. We're also going to look at the reactivity of aldehydes and ketones before we go on to the next part of this chapter, which is the reactions of aldehydes and ketones. Aldehydes and ketones tend to react with nucleophiles because of the positive charge, shown here, of the carbonyl carbon. Nucleophiles themselves can either be strong and basic or weak and basically very low basicity. Strong nucleophiles are strongly basic and they usually have a negative charge. That negative charge is attracted to the partial positive on the carbonyl carbon, and the nucleophile makes a bond. Now, when it makes a bond, in order to make room for this additional bond on this carbon, we're going to break the pi bond and push those electrons out onto the oxygen so that we get an intermediate which looks like this. This turns out to be an extremely important structure in organic chemistry. It's even given a special name. It's called the Tetrahedral Intermediate, probably because we start with a trigonal planar carbonyl, and once we add another bond to it, giving it a steric number of 4, it becomes tetrahedral. The important thing about the tetrahedral intermediate is that it is extremely unstable because this negative charge on the oxygen is going to create what we call electron pressure, repulsion from those electrons, pushing out against the other bonds. If we form a tetrahedral intermediate then, where there is a good leaving group attached to the carbonyl carbon. So for example, chloride, which is a reasonably strong nucleophile, could potentially make a bond to the carbonyl carbon, push a pair of electrons out of the way, and create this tetrahedral intermediate, where we have a negatively charged oxygen and a chlorine atom directly attached to the same carbon. What happens in this case is that the electron pressure from the oxygen will push down toward that central carbon, and because the chloride is a good leaving group, it will push that bond back out onto chlorine, reversing the reaction. And therefore, although chloride ion could add to a C double bond O, when we actually do this in the laboratory, we see that we generally don't get any products because although it adds, it's rapidly pushed back to the reactants. In general, what we see is that if we have any group other than a carbon group or a hydrogen attached to that tetrahedral carbon, it can be pushed off. If there is more than one possible leaving group, the least basic group will be pushed off, so we would want to go to our pKa table and look in the base column and find the group that is the highest up in the right-hand column, in other words, the weakest base. That would be the preferred group to leave. If we look at weak nucleophiles, there are several different types of weak nucleophiles, the most common of which are alcohols and water. If we look on the pKa table, these are very high up on the pKa table in the right-hand column. So they're really excellent leaving groups, but they are also reasonable nucleophiles. They generally are uncharged, and so they have a much less strong attraction to the carbonyl carbon. Finally, because these weak nucleophiles are good leaving groups, if they do make a bond to the carbonyl carbon, as shown in this example here, where we have methanol coming over using a pair of electrons to make a bond, pushing a pair of electrons from the central carbon out onto the oxygen, we get a tetrahedral intermediate that looks like this. But unfortunately, because of the electron pressure, that oxygen negative will push a pair of electrons back down toward the center and push out the alcohol as a leaving group. And so when we look at the equilibrium, the product side is very much disfavored. We generally don't get products from this. What we're going to do is we're going to use acid catalysts to help these weak nucleophiles react and stay attached to the carbonyl carbon. So what we're going to put in is a strong acid, and we will talk about some of those strong acids later on. By putting in the strong acid, we will change the mechanism. Generally, when you have an acid mechanism like this, the first step will be an acid-base reaction because acid-base reaction is a very rapid reaction. So in this case, as we talked about, the hydrogen is going to be an electrophile. It's going to be attracted to electrons. We saw that electrophiles prefer to react on the oxygen, which has a partial negative charge. So one of the lone pairs from the oxygen will come over and it will make a bond to the hydrogen. That's going to create this intermediate. This is a protonated carbonyl. Now, when we protonate the carbonyl then, we will see, if you did the resonance structures for this, you would see that the carbon plus resonance structure becomes much more competitive because of the nature of the formal charges. So therefore, effectively, this partial positive becomes larger. That larger partial positive charge helps attract this weak nucleophile. So now the weak nucleophile is going to attack more often, more rapidly. When it does attack, it will still push a pair of electrons out onto the oxygen. But what we will get is this intermediate. And if you look, this is a protonated form of the tetrahedral intermediate, where the oxygen no longer has a negative charge, and therefore there's a greatly reduced amount of electron pressure. That will allow this strong leaving group to stay attached long enough for other things to happen. The last thing I want to talk to you about in this section is the relative reactivity of aldehydes and ketones. This becomes useful sometimes in synthesis. We find that generally aldehydes are more reactive than ketones when we're trying to add nucleophiles. There's two reasons for this. The first is that if we look at the size of the two groups attached to the carbonyl, comparing them in an aldehyde to a ketone, we can see that the aldehyde has one pretty large carbon group, but then a very small hydrogen. So that makes it less sterically hindered than a ketone where we would have two large carbon groups. Because of the increased steric hindrance generally slows down nucleophile reactions, so that's going to make the ketone reaction slower than the corresponding reaction with the same nucleophile on an aldehyde. The other interesting thing is there's an electronic effect. When we look, we can see that an aldehyde in its reactive resonance structure, the resonance structure that has effectively a carbocation on the C double bond O carbon, has only one carbon group attached to that carbocation. In contrast, when we look at the ketone resonance structure, it has two carbon groups. If we recall from our discussion of nucleophilic substitution and carbocation stability, carbon groups are electron donating when compared to hydrogen. So the aldehyde has only one electron donating carbon group to stabilize this carbocation like structure, whereas the ketone has two. Because the ketone has two electron donating carbon groups, that effectively makes the partial plus smaller in the ketone than it is in the aldehyde. So again, nucleophiles are going to be less attracted to the ketone. The aldehyde should react faster. That's the end of this section of video. We're going to move on to look at the reactions of aldehydes and ketones next.